As we continue our studies of the properties of water, let's review together the hydrophobic effect. As we will see, it's not just the power of water to attract that makes it the biochemical solvent, but also its power to repel. I'll just take a moment to remind you of the two opposing tendencies of molecules as they interact with water. Some compounds readily dissolve in water and are therefore hydrophilic or water-loving. These would include ionic or charged substances, as well as those that are uncharged but polar. Hydrophobic molecules are water-insoluble, and examples include hydrocarbons like hexane or other alkanes. Rather than associate with water, hydrophobic compounds tend to aggregate with each other. There is a third class of compounds that are neither entirely hydrophilic nor entirely hydrophobic. These molecules contain separate regions that exhibit each tendency. A good example of this is the fatty acid palmitate pictured here. It has a polar domain in the charged carboxyl group and a nonpolar domain in its long hydrocarbon tail. Note that most of the surface area is the portion that is nonpolar, and for this reason it is insoluble in water. Just as there are degrees of polarity, so there are degrees of nonpolarity. The greater the nonpolar surface area, the more nonpolar the compound. Being mostly hydrophobic in surface area, amphipathic molecules tend to aggregate together in various ways depending on the geometry of the molecule. In the case of fatty acids like palmitate, they associate to form micelles, as illustrated here. In this arrangement, the nonpolar tails are buried on the inside, away from water. The polar head groups associate on the external surface in direct contact with water molecules. Recall from an earlier lesson that the nonpolar regions are involved in interactions due to induced dipoles. We'll look at the thermodynamics of these associations in a later lesson. For now, just realize that much of the interactions of biomolecules has to do with the hydrophobic effect.